Hey, hello everyone. So thanks for joining in today. It's good to see the community here. So today I'll be covering on the how do we optimize storage performance and how do we essentially build efficient index configurations for OpenSearch. So just to give a brief intro about me, I'm Mohit. I have been an OpenSearch contributor since last 3 years or so. I work with Amazon as a software development engineer where I work with indexing as my primary area of interest. So so we are talking about this performance and all, but let's first try to understand why it's important, right? So today, say when we started, it took around 3 days to ingest 8 dB of web access logs data on a setup like 4 vCPU, 3 data nodes. And for better observability, right? So when you're working on, let's say, an incident response or something, you want your data to be available immediately so that you are able to get insights out of it, get to the root cause, mitigate your issues, right? How do we bring that time further down so that you are able to ingest the data faster, see it faster, and also reduce the cost for the same? So targeting the observability use case, it becomes very important to keep the performance and efficiency of OpenSearch in mind. And in order to basically do this for the users, we have had this journey for like last 1.5 or 2 years where we have worked on quite a few performance improvements. And before I dive into those improvements, let's first try to understand how indexing actually works in OpenSearch. So as a user, you send a request. It can be a bulk request with a batch of documents. It can be a single document. You send it to OpenSearch. Based on the index it is coming for, OpenSearch decides which shard it should go to. It has an automatic shard routing based on the ID it generates, or you can provide it how to route it as well if you are looking for some co-locality of data. And then this node which does all this work is the coordinating node. Once it is decided, the coordinating node forwards that document or the batch of documents to the specific shard it should go to. And what happens there is the entire document, let's say the JSON document that you have provided, it's parsed into the specific Lucene fields, so that using those fields, we can create whatever data structures we need, be it an inverted index or a columnar format if you want to, let's say, perform aggregations or sorting on it, or just store it for, let's say, retrieval at a later point of time. And on these data nodes, when these fields are generated, essentially the data is converted into something called as Lucene segments. And we actively keep writing to these Lucene segments unless there's a point called refresh, OpenSearch refresh. You all must have used that. And at that point, the data is basically available for search. And in the meanwhile, until that point, we store the data in a write-ahead log called translog as well, so that it's persisted, so that in case your process goes down due to some issues, it's still available on disk. And also, we do replicate the documents from essentially one node to another, so that even if there is a hardware failure or you are facing some outage in some availability zone, the data is still available for searching and ingestion. And while I talk about this, how do we actually go about analyzing the performance of this, right? So I know this is not readable for sure, but I think for anyone who is working on performance, this is something called a flame graph, and essentially these are very useful in analyzing how much CPU cycles, how much memory allocation is happening on each part of the code. And while we were trying to figure out what performance improvements to do, we used these tools quite a lot. We basically went into the depths of OpenSearch to try to figure out how we can squeeze that entire 1%, 2% CPU out and basically make OpenSearch better. In order to basically, so based on our analysis, we delivered quite a few improvements. So for example, if you are a heavy user of metrics use cases, you will be dealing a lot with the floating point numbers. So the floating point number parsing that happens by default in JDK, we found that it was slow compared to the alternatives available. And to our luck, Jackson already had an implementation for that parsing, which we were able to leverage. And say for use cases like vectors or metrics, right, where the data is mostly filled with floating point numbers, we were able to see a lot of good improvement in document parsing. And specifically in the overall macro throughput improvement, we could see it improving by overall 5%. Similarly, date time fields are always part of your documents for any time series data. And again, so the JDK datetime parsing is designed so that it is able to support a variety of use cases. But given that you may have fixed width formats for datetime. Usually, we were able to figure out that, okay, if we know what the format is specifically, we can go bit by bit, byte by byte, and make basically better parsing decisions and not need the entire allocation and all which JDK parsing needed. Again, with this, we were able to see a 5% throughput improvement on the workload that we tried. Post that, there were also, I think, so Intel contributed something called a Zstd to OpenSearch, which was very useful for overall storage reduction that we see compared to the LZ4 algorithms, while providing same or better ingestion performance at the same time. So one good thing about this was it provided double the things, right? Your storage reduced and your performance improved as well. So essentially, it's doing more compression, but the question is like, it should be using more CPU, right? But the good thing about this modern algorithm is that it's the P50 latency for the compression that ZSTD provides is not too high when compared to a fast algorithm like LZ4. But at the same time, what it does is it makes your segments very smaller so that the background operations which need to happen later on segments to compact them, to make them easier or faster to search, it makes those operations faster as well because your data is quite compacted already now. And that provides you a further indexing improvement as well. Along with this, we did work on the memory side as well to reduce the allocations which happened during the document parsing, and also a lot of operations based on reflections which were happening to account for the memory which translog uses and all. And these were quite small changes here and there, which we figured out using the flame graphs that I showed, the dumps we took, heap dumps we took, and the thread dumps we took, and we were able to improve on these further. Again, we are also looking into use cases where users are using OpenSearch for, let's say, events data like ticketing and all, where they see quite a lot of updates happening in their document. And in such cases, we found that there was a lot of time just going into figuring out what the document's earlier version was before you could update it. So thinking along those lines, we introduced something called as Bloom filters for the document, optimizing the document ID lookup. And for absurd kind of workloads, where we are doing a lot of inserts and updates, we could see that there was an overall improvement of 30% performance in the overall indexing. And also for the gets that you now need to do on the doc ID itself, right? The term queries which will go on the document IDs, you will see improvements there as well of the same order. And this does account for a slight storage overhead, but given the kind of performance improvements based on the trade-off you'd like, it provides basically a good view into how you can improve the performance of your upserts. Again, we also looked into the tail latencies, how they were functioning. So not just the P50, P90s, and the time when your burst workloads are happening, right? It's difficult to scale for that, and your tail latencies start impacting you a lot there. So we also looked into that aspect, and we tried to optimize tail latencies by figuring out what was contributing to it. So for example, in this case, the flush process that happens in OpenSearch, which is actually persisting the data from active in-memory segments into the immutable disk segments. At that point, we saw that write threads were contributing quite a lot to help out with those flushes. So we leveraged Lucene features there, improved our integration with that to expose a setting, which allows you to optimize how to use those write threads and not use them for flushes, but instead use them for active writes which are coming in. So yeah, based on this, overall, we could see that we started somewhere, let's say with a 1x performance, and at the end of all of it, we were at 1.57x improvement, right? So that's quite an improvement, but all of you must be thinking like, okay, all of you can see this here in these slides, but may not have seen it practically, right? How do we ensure that, okay, these are basically available to you on your workloads as well? So yeah, the weird thing about performance tuning for a database like OpenSearch is that OpenSearch supports a variety of use cases, right? So for example, let's say something like a Bloom filter. If you're not doing any update operations, it may not make a lot of sense for you to pay for that extra storage which comes for it, right? So it can't be a default. So because of these variety of use cases, users have to opt in to use those features. And OpenSearch has over 150 or so index settings. So there are a lot of granular tuning knobs that are there, which you need to basically go through, figure out what suits your use case, what doesn't suit your use case, right? And in turn, it requires a lot of in-depth knowledge requirement around not just the core, but also other features. So all of you who are using OpenSearch for, say, logs kind of use cases must be dealing with rollovers, tiering, deletion of old data. And again, you're required to set up policies, you're required to manage those policies, right? And it requires in-depth knowledge, not just for the core, but for the entire ecosystem which is built around the core OpenSearch using these plugins. And with every feature, the community is innovating a lot to come up with more features. And with every release, you are getting new and new index settings, new and new cluster settings, and they get lost in the sea of documentation, right? And just to figure out which works for you, which doesn't work for you is, again, a lot of work and acts as an entry barrier for you to even use OpenSearch. Again, also to add to that, there are some features which can be applied, but there is no unified schema, let's say, for which all the users who use OpenSearch follows. For example, let's say you are ingesting Kubernetes logs. You may be having a different mapping schema than what someone else is using. So even providing the defaults based on the mappings, like which data structure should be created or not for what field, it becomes difficult for an operator of OpenSearch to provide, right? So let's talk about how to solve for it, right? So basically, if we can gain some information about what use case we plan to basically create the index for, it becomes easy to decide internally within the OpenSearch server system to decide which configurations to apply and which not to. So for example, let's say if I know that you're going to use updates, it makes sense to have Bloom filter so that your overall performance is faster. And once I'm aware of the use case, it becomes easy to provide a bundled way so that all the settings, the 150 settings, whatever is the subset which suits your use case, can be applied. And in turn, it makes the entire index management easy for all the users, right? And not just that, like when a new feature comes in OpenSearch, right, in future, how do we ensure that even that is available to the existing users without them needing to, let's say, opt in for it explicitly? So in order to solve for this, what we have come up in OpenSearch with is application-based configuration templates. So what are these essentially, right? So these are system templates which basically come up with a sensible default and a defined schema. These are immutable templates which you can use. And once you use this, you should be able to get a lot of bundled features out of the box for you. So it is essentially aiming to ease the onboarding process of OpenSearch for users so that they don't have to tune a lot. So for example, let's take this example where I'm creating a metrics index. I'm providing Zstd as a codec so I get good compression. I'm providing log byte size as a merge policy so that my data is my temporal data is co-located together. Refresh interval is 60 seconds so that I'm not creating a lot of small segments. Replication type as segment so that I'm able to utilize my system better for indexing throughput. And then check pending flush.enable so that my tail latencies are lesser, so that write threads are not helping a lot on the flushes. Knowing about all these 5 settings, right, it's definitely cumbersome. What if I could replace it with something like this? You create a metrics index, you just say what is the context of this index is metrics, and by default, in the background, all of these settings get applied to you. If you are logs use case, there will be a separate set of settings which get applied. If you're an events use case, there will be a separate set of settings which get applied, but you just have to care about what the use case is, and OpenSearch takes care of all of this all in the background. Yeah, so just to cover how they are modeled today, right, in OpenSearch, these templates. So these are versioned so that every time a new minor release or a major release happens for OpenSearch, we are able to add new features without breaking the existing indices or index templates that you have. And we are aiming to provide a managed experience with this. So what I mean by this is that whatever is declared in the template, if that overlaps with what you are trying to provide, we'll honor the setting which is provided by the template here. And we are also planning to have the parameterization support in this so that if we know that some feature which is going to help the use case, but we still don't know the schema. Let's say, for example, I want to declare some searchable fields as the default so that I can provide basically just that key as a setting, and that when you create an index, you can provide the parameters in the context to fill that so that it acts as a forcing function so that you get the goodness of that feature as well, where we cannot decide without a lack of schema. Yeah, so just to give a brief overview of how this is used, right? So ABC templates, or the application-based configuration templates, they use component templates as a storage model. And based on this storage model, basically they can be used in index as well as index templates through something called as context, which I showed in the previous slides. So we are still reusing the basically foundational constructs which exist today in OpenSearch, but adding some application logic on top of it so that it's easy for users to get these use cases out. And to add to it, we have also exposed this as a plugin, so that if you basically are an operator of OpenSearch and you want to provide these plugins to you, these templates or custom use cases which we may not have thought of to your users, you can extend this plugin and add more use cases as you need. Yeah, so this is a feature which we have already launched in basically OpenSearch 2.17 as an experimental feature. All you have to do is you need to install the plugin and enable the feature flags for now, given it's an experimental feature, and you should be able to use it. You can go to the documentation to read more about how it works and how you can use it. And I'm looking forward to listening to questions from you or on the forum or GitHub issues or any discussions that you may want to have. Just to give an idea of what already exists today in terms of the use cases, right? So we have started with few of the generic use cases like logs and metrics, where we have provided certain settings which you should be able to use if you onboard to the context feature. And we also have provided some schemas along with the performance tunings for use cases like Nginx, Kubernetes logs, Apache Web logs, and some of the Amazon services logs, which essentially you can use, and you get the schema based on the OTel or ECS schema, and along with the performance improvements that come with the application-based configuration templates. Yeah, so now that we are here, I would also like to talk about what we are planning in the future for this. So yeah, so the next goal for this is to make this feature generally available, and it would be great for the community to try it out, let us know what's lacking, what they would like more in it, so that we are at a state where we can make it generally available for everyone. And in terms of the API compatibility, in terms of the UX for this and all. And we are also planning to see what all more features or what all more templates we can add here. So for example, the parameterization support that I talked about, right? We are actively looking into how to implement it and make it available so that we can enforce feature usages where we believe it may help. And now that we have this templates and the index context as a building block to allow more features to be built and adopted easily, right? We are also looking into quite a few performance improvements which we would like to contribute. So next I'll cover those improvements as well. So one of the areas that we are exploring actively is how to improve the storage usage for your OpenSearch indices. So lesser storage definitely translates to lesser costs. So your SSDs or your remote store, the lesser data you store on SSDs, it's cheaper. The lesser data you store on your remote stores, it's again easy to basically interact with it in terms of latencies. Although the storage itself is cheaper, the interaction becomes cheaper again because you don't have to make as many calls to fetch that entire data. And all the background operations which happen, right? Refreshes, flushes, the reads which needs to happen. Those IOPS heavy operations, we also want to see once the storage reduces, we should be able to see that interaction with the entire IO system that we have, right? That to reduce. And that what it allows is, again, the lesser you pay for the storage, more you are inclined to keep your data available right, based on your use cases. So what we are exploring in the storage optimizations are basically how we can reduce the size of the source field which gets stored today. So source field is essentially the entire document that the user sends in. We stored it as a stored field in a row-wise fashion so that it can be retrieved later for needed by users or for use cases like reindexing. So we are looking into how we can do away with it and use the existing data structures that we have to provide better storage usage. And we have seen certain use cases where the source field storage itself takes about 50% of the index size. So we are trying to see how we can improve this further and maybe get away with it at all if we are able to. We're also looking into exploring things around columnar data, which is the doc values that you may have configured for your fields, and how we can compress them better based on the data types. So how we can, let's say, do it for floating point numbers, or what we can do different for keyword fields, ordinals, right? We are looking into the same as well. And we are also looking into how we can improve our integration with Lucene to decide which data structures to create or not. So for example, today, for a keyword field, you create both index and doc values, right? So with the earlier introduced concept of templates, right? If I know the schema and if I know that some field is essentially not essentially going to be just, let's say, a metric and not a dimension for your metric kind of use cases, the inverted index may not make a lot of sense. You may be able to do a lot of work with doc values, right? So how we can improve that integration through the templates so that you don't create the data structures if you don't need it. And again, it translates to improved storage costs. Apart from this, we are also working on how we can improve the query performance. So one of the major use cases that we are covering here is the aggregations. So what we are planning to do is we are introducing star tree for efficient aggregations and providing predictable performance. So with this feature, we are planning to create a pre-aggregated view using the star tree data structure so that the storage overhead is not as high as a complete materialized view. It just adds a slight overhead, but still provides you a predictable performance and helps you do away with the... So today, aggregations take latencies in the order of number of documents that they have to visit. How we can reduce it further with the pre-aggregated views is the goal. And the initial results that we have seen look quite promising. So for example, here you can see, right, for, let's say you are doing a metric aggregation for ELB, for the target status code as 200. If there are 200 million documents, the plain query takes 4.2 seconds, whereas the query with the star tree takes 2.5 milliseconds, right? So the pre-aggregated view is providing these kind of performance improvements with a slight storage overhead. And basically, and all of this is happening in real time, again, when compared to, let's say, something like a roll-up feature that we have, which continuously needs to poll and keep it updated with the actual index. So we are doing all of this within the core during the flush process in OpenSearch itself, so that when the segments are created, you get this straight out of the box. And we are actively working on the changes around index configuration, data structure creation, and basically building the search flow for this, so that it's essentially easy and it's essentially faster for your queries. And as next steps, we'll also try to see how we can onboard this to the earlier covered ABC templates concept and make it available to the users or make it more visible to the users. The other things that we are looking at is, for example, the performance optimization is co-locating similar data together for better compression and data access patterns. So what we are trying to do here is essentially grouping the similar data in same segments. So for example, let's say you're ingesting access logs data, and you may have status codes, different status codes, right? 200, 400, 500. And if most of the cases during an incident, you are going to look for, let's say, 500 as a status code or 400, right? Why do you need to go through the data which contains 200 as a status code? So if we can divide the data in the segments such that 400, 500 are separate, 200 is separate, we need to go through a lot less documents in segments to get the same result out and get the improved latencies. So we are working on how to expose this as a configuration to users of OpenSearch, and also doing the core changes within Lucene to basically create the segments in a way that they are bucketed by default. So this is essentially kind of a bucketing which we are doing. And we have been seeing quite promising results, both in terms of the query performance and also the storage use, because when you store similar data together, it by default compresses better on how Lucene is written. So we are actively working on this as well, and Rishabh is someone who is actively looking into it. We are also looking into how we can support append-only indices in OpenSearch. So for those of you who may have attended Fro's talk yesterday around search performance, deleted documents add quite a lot of overhead in terms of what basically we do when we do query optimizations, right? So if we know beforehand that indices are supposed to be append only. We're looking into what kind of optimizations we can build. For example, let's say we don't have to support soft deletes for those indices, which makes the overall ingestion faster. We don't need few fields there. Again, the query part itself, we can by default know that, okay, a lot of performance optimizations on the query side, which are hindered today by deleted documents, will go away. And we are actively working on this as well. Yeah, so that was what I wanted to share yesterday. Today. Yeah, open to any questions.